Speed defines the very structure of our universe. This is a journey to the absolute limits of velocity, where the fastest objects in existence reveal a cosmos far more dynamic and violent than we often picture. We will explore a spectrum of speed demons, from ghostly particles moving at nearly the speed of light to entire galaxies hurtling away from us faster than light itself. Understanding these extreme velocities is not just about impressive numbers. It is the key to unlocking the universe's deepest secrets, from the warping of spacetime to the ultimate fate of all things. By the end, you will grasp how these incredible speeds shape everything we see, testing the laws of physics as we know them. We will uncover what propels a dead star across the galaxy like a cosmic bullet, and ask how something can appear to move faster than light without breaking the universe's ultimate rule. What do you believe is the ultimate source of power in the cosmos? Our universe does not operate without rules. At its very foundation lies an absolute, unbreakable law, a cosmic speed limit set in the fabric of reality itself. This is the speed of light in a vacuum, a constant represented by the letter c, a figure so fundamental it appears in the most famous equation of all, E equals mc squared. Light and all massless particles like it travel at this ultimate velocity, approximately 299,792,458 meters per second. For anything with mass, this speed is a barrier that can be approached but never, ever reached. To push an object with mass to light speed would require an infinite amount of energy, a physical impossibility. This limit is not a suggestion or a technological hurdle. It is woven into the geometry of spacetime, a cornerstone of Einstein's theory of relativity. It dictates how cause and effect work, ensuring the logical order of the universe. And it is precisely this ironclad rule that makes the objects we are about to explore so breathtaking. They are the universe's ultimate daredevils, pushing as close to that forbidden line as physics will possibly allow. Their existence forces us to ask what phenomenal forces could possibly accelerate something to such a staggering fraction of the universe's maximum speed. To approach that forbidden speed, we must look to the most powerful engines in the known universe, supermassive black holes. These gravitational monsters anchoring the centers of galaxies are not just cosmic vacuums. In their most active state, they become nature's ultimate particle accelerators. As immense quantities of gas and dust spiral inward in a structure called an accretion disk, friction heats the material to millions of degrees. But not all of this doomed matter falls into the black hole's event horizon. A fraction of it gets channeled, focused by unimaginably powerful magnetic fields, and blasted back out into space in the form of two narrow, opposing beams. These are relativistic jets, colossal fountains of superheated plasma stretching for thousands or even millions of light years. The particles within these jets, electrons and protons, are accelerated along magnetic field lines with such ferocious efficiency that they reach over 99.9% of the speed of light. We can actually observe the consequences of this extreme velocity from Earth. Because the jet material is moving almost directly toward us at such a fantastic fraction of light speed, the light it emits later has less distance to travel to catch up to the light emitted earlier. This creates a cosmic illusion, making it appear as though blobs of plasma in the jet are moving faster than light across the sky, a phenomenon known as apparent superluminal motion. It is a stunning visual confirmation of relativity in action. These jets are more than just a spectacular light show. They are fundamental architects of the cosmic landscape. They transport immense energy across galactic distances, heating intergalactic gas, suppressing star formation in entire galaxies, and seeding the vast voids between galaxies with high-energy particles. They are the universe's own particle accelerators, operating on a scale and at a speed that human technology could never hope to replicate. Yet the raw power of a black hole's jet is not the only way to achieve such extreme velocity. Some of the fastest solitary objects in our galaxy are born not from ongoing acceleration, but from a single catastrophic event, a stellar death that imparts a ferocious kick. These are pulsars, the rapidly spinning, ultra-dense cores left behind when a massive star explodes in a supernova. A neutron star is a city-sized object with the mass of our Sun crushed into a sphere only about 12 miles across. A single teaspoon of its material would weigh as much as a mountain. When such a star collapses, the explosion is rarely perfectly symmetrical. Even a slight imbalance in the detonation can act like a rocket nozzle, launching the newborn stellar corpse across space at breathtaking speeds. This is known as the pulsar kick. One of the most famous examples is the pulsar known as PSR 2224+65, which is carving its way through space at over 1,000 kilometers per second. Its journey is so fast and its path so dramatic that it has created a bow shock in the interstellar gas ahead of it, a glowing structure that, from our vantage point, resembles the shape of a celestial guitar, earning it the name the Guitar Nebula. We can measure these incredible speeds by observing a pulsar's proper motion. Its tiny but perceptible shift against the backdrop of more distant stars over years or decades, combined with the precise timing of its lighthouse like radio pulses. These measurements reveal pulsars not as stationary beacons, but as cosmic bullets streaking through the voids between stars. Their journeys are lonely and immense, often destined to eventually escape the gravity of the Milky Way entirely, becoming intergalactic travelers cast out from their birthplace. Each one is a tombstone and a testament, a remnant of a star that died violently, and a navigational marker hurtling through the dark, its rapid spin and immense magnetic field broadcasting its passage for eons. But a stellar corpse is not the only thing that can be flung from the galactic center. Entire, living stars are also being violently evicted, destined for a journey into the endless dark between galaxies. These are hypervelocity stars, and their discovery rewrote our understanding of the Milky Way's core. Imagine a binary star system, two suns orbiting one another, drifting too close to the supermassive black hole at the heart of our galaxy. The immense tidal forces of the black hole can tear that partnership apart. In a gravitational slingshot of staggering violence, one star is captured into a tight orbit around the black hole, while its former companion is catapulted outward at a speed that can exceed 1,000 kilometers per second. This is not a gentle nudge, it is a cannon shot. That ejected star is moving so fast that it overcomes the entire gravitational pull of the Milky Way galaxy itself. It becomes unbound, a runaway sun on a one-way trip out of our stellar city. The first of these stars was discovered only in 2005, a solitary blue star racing away from the galactic center at over 850 kilometers per second. Since then, more have been found, each a testament to a dramatic encounter with the black hole we call Sagittarius A star. Their journey is profoundly lonely. They will leave the bright spiral arms and star clusters of the Milky Way far behind, venturing out into the vast, nearly empty intergalactic medium. For billions of years, they will travel through profound darkness, their light a solitary beacon in a sea of nothing, until their fuel is spent and they fade away. These stars are more than just celestial speedsters, they are living probes. By tracing their paths backwards, astronomers can map the gravitational environment of our galaxy's inaccessible core. Their very existence confirms the presence and ferocious power of the supermassive black hole, acting as cosmic messengers sent from the most chaotic region of space, carrying the signature of its gravity in their incredible speed. But even the black holes themselves are not immune to being thrown from their thrones. The most massive objects in the universe can also become the fastest, in a phenomenon that sounds like pure science fiction: runaway black holes. This incredible process begins when two galaxies, each with a supermassive black hole at its core, collide and merge over billions of years. Their central black holes eventually sink to the new galaxy's center, forming a binary pair that begins a slow, spiraling dance of death. As they orbit closer and closer, they warp the fabric of spacetime itself, sending out ripples known as gravitational waves. These waves carry away tremendous amounts of energy and momentum. If the merger is perfectly symmetrical, the waves radiate evenly in all directions, and the resulting single, larger black hole sits calmly at the center. But if the merger is lopsided, if the black holes have different masses or spins that are not aligned, the gravitational waves shoot out more strongly in one direction. According to Newton's third law, for every action there is an equal and opposite reaction. The intense, one-sided blast of gravitational waves acts like the thrust from a rocket engine, kicking the newborn black hole clear out of the galactic core. Computer simulations of these violent events show the recoil can be unimaginably powerful, propelling a black hole with millions of times the sun's mass at speeds that could reach 5,000 kilometers per second. At that velocity, it would cross the entire Milky Way in just a few million years. Detecting an invisible object moving that fast is one of astronomy's greatest challenges. A lone black hole, unless it is actively feeding, gives off no light to see, but its passage is not completely silent. Its immense gravity would distort the light from stars behind it, a telltale signature called gravitational lensing. It might also drag a retinue of stars that were tightly bound to it, creating a strange, fast-moving cluster streaking through the galaxy. Or, if it plows through a cloud of gas, the sudden compression could trigger new star formation in its wake, leaving a trail of young, blue stars like breadcrumbs marking its path. Finding such an object would be a direct confirmation of Einstein's predictions in their most extreme form. A silent titan fleeing the scene of its own cataclysmic birth, carrying the echo of that collision in its incredible speed. But speed is not only a property of the most violent explosions or the most exotic objects. It is woven into the very fabric of our cosmic home. Every star you see in the night sky, including our own sun, is in a state of constant, graceful, high-speed motion. We are all part of a grand celestial whirl orbiting the heart of the Milky Way galaxy. Our sun, with its entire planetary family in tow, travels at a serene yet staggering 230 kilometers per second along its galactic path. That is over 500,000 miles per hour. At this velocity, we complete one full orbit around the galactic center roughly every 225 million years. This period, the length of our galactic year, provides a humbling sense of cosmic time. The last time our solar system was in this particular position in the galaxy, the dinosaurs were just beginning their long reign on Earth. This motion is not unique to us. It is the defining characteristic of a spiral galaxy like our own, a vast pinwheel of billions of stars all tracing their own orbits around a common center. But here is where the story takes a mysterious turn. When astronomers first calculated the speed of stars based on the visible mass of the galaxy, the stars and gas we can see, the numbers did not add up. The outer stars in the Milky Way's disk were moving far too quickly. According to the laws of gravity, with only the pull of the visible matter, these distant stars should be orbiting much more slowly, like planets farther out in our solar system. The fact that they are not tells us something profound. There must be an immense amount of unseen matter, a vast halo of something we cannot detect with telescopes, whose gravity is holding the fast-spinning galaxy together. This invisible glue is what we call dark matter, so the very speed of our sun's journey and the velocity of every star in the Milky Way is not just a fact of our location. It is a fundamental clue, a piece of evidence written in motion, pointing to the existence of a shadowy component that makes up over 80% of the matter in the universe. Our graceful whirl through the galaxy is in fact a silent testimony to the universe's greatest unsolved mystery. Yet our galaxy's graceful whirl is only part of a much larger, more urgent journey. The entire Milky Way, along with our neighboring galaxies in the local group, is caught in a colossal river of motion, a headlong rush through the cosmos at an astonishing 600 kilometers per second. This is our bulk flow, and we can measure it against the oldest light in the universe, the cosmic microwave background radiation. This faint afterglow of the Big Bang serves as the ultimate stationary backdrop, a universal reference frame. When we look at this ancient light, we see a subtle distortion, a Doppler shift, because we are moving so quickly through space. This tells us we are not merely orbiting our galactic center, we are being pulled irresistibly toward something immense. For decades, astronomers knew we were speeding toward a mysterious concentration of mass hidden behind the dense stars and dust of our own Milky Way's central plane. They called it the Great Attractor. It is a gravitational anomaly so powerful it is drawing our entire galactic neighborhood toward it. Imagine the Milky Way as a leaf caught in a vast, invisible current, flowing toward a distant waterfall we cannot yet see. The Great Attractor is not a single object, but a massive overdensity of galaxies, a knot in the cosmic web with the combined pull of tens of thousands of Milky Ways. But the story does not end there. Our motion toward the Great Attractor is itself just a component of an even grander flow. We, along with the Great Attractor, are all being pulled toward something even larger and more distant, the Shapley supercluster, the greatest concentration of matter in our observable universe. This is our true destination in this cosmic river. So every second, our solar system moves 230 kilometers around the galaxy, while the entire galaxy itself hurtles 600 kilometers toward the heart of the universe's largest structure. This layered motion paints a humbling picture. We are not passive residents of a static universe. We are participants in a dynamic, rushing architecture where galaxies themselves are mere travelers, following the gravitational pathways of an invisible scaffold that spans billions of light years. Our high-speed trajectory is a direct map to the hidden concentrations of mass that shape the cosmos, a reminder that even the grandest motions we have discussed are just local currents within a universal tide. But the most elusive speed demons are not massive stars or black holes. They are the smallest pieces of matter imaginable, arriving from the depths of space with energies that defy belief. These are cosmic rays, and they are not rays of light at all, but subatomic particles, primarily the nuclei of atoms, stripped of their electrons and hurled across the universe at velocities indistinguishable from the speed of light. They are a constant, invisible rain, with trillions passing through your body every second, though most are low-energy particles from our own sun. The true mysteries are the ultra-high energy cosmic rays, the rarest and most powerful particles in nature. Their energy is so immense it must be described in units beyond our everyday experience. In October 1991, a detector in Utah registered an event so extraordinary it was named the Oh My God particle. This single subatomic particle, likely a proton or an atomic nucleus, hit our atmosphere with the kinetic energy of a professionally thrown baseball, all packed into a speck smaller than an atom. To achieve that, it must have been traveling at 99.999999999999995% of the speed of light, a number so close to the ultimate limit it is almost incomprehensible. For a brief instant, that one particle carried energy millions of times greater than anything produced by our most powerful particle accelerators like the Large Hadron Collider. The existence of such a particle presents one of astrophysics' greatest puzzles. What cosmic engine, what natural particle accelerator, could possibly fire a single proton with such ferocious force? The candidates are the universe's most violent phenomena. Active galactic nuclei with their relativistic jets are prime suspects, capable of accelerating particles along magnetic fields for millions of light years. Cataclysmic events like gamma-ray bursts, the birth cries of black holes or collisions of neutron stars, release more energy in a few seconds than our Sun will in its entire 10 billion-year lifetime, and could potentially generate such extreme particles. Yet even these incredible sources struggle to explain the very highest energy events. There is another, more profound mystery. Particles with such incredible energy should not be able to travel vast cosmic distances at all. Space is not completely empty. It is filled with the faint glow of the cosmic microwave background radiation, the afterglow of the Big Bang. An ultra-high energy proton racing through this sea of ancient photons should collide with them, losing energy bit by bit over distances greater than about 150 million light-years. This is known as the Greisen-Zatsepin-Kuzmin, or GZK, cutoff. The oh my god particle and others like it appear to have too much energy, suggesting they came from relatively nearby in cosmic terms. But when we look in the direction it arrived from, we see no obvious cataclysmic source within that limited volume of space. So the puzzle deepens. Where did it come from and how did it get here? Each of these ultra-high energy cosmic rays is a messenger from a cosmic catastrophe, a calling card from an event of unimaginable power, carrying its secret encoded in its impossible speed. While cosmic rays arrive from deep space, our own star is capable of unleashing bursts of particles at near light speed right in our cosmic backyard. The sun is not a placid ball of fire, but a churning magnetic dynamo, and when those magnetic fields become tangled and snap, they trigger the solar system's most powerful explosions. A solar flare is a sudden, intense flash of radiation across the electromagnetic spectrum, from radio waves to X-rays. This flash is the visible sign of a catastrophic magnetic reconnection event, where twisted magnetic field lines cross, break, and violently reconnect. In that instant, a colossal amount of stored magnetic energy is released, accelerating electrons in the sun's corona to over 99% of the speed of light in a matter of seconds. These relativistic electrons then spiral down magnetic field lines and slam into the denser solar atmosphere below, producing the brilliant flash we observe and a storm of high-energy radiation. It is a particle accelerator the size of a star operating in a heartbeat, but the violence does not stop with light. Often accompanying a major flare is a far more massive, though slower, eruption called a coronal mass ejection. Imagine not just a flash of light, but the sun itself tearing off a piece of its outer atmosphere and hurling it into space. A CME is a billion-ton cloud of superheated plasma, a soup of protons and electrons embedded in a magnetic field, blasted away from the sun at speeds ranging from 250,000 to over 3 million kilometers per hour. While slower than the electrons in a flare, this is still an immense velocity, allowing a CME to cross the 150 million kilometer gulf to Earth in as little as 15 hours. The true power of a CME lies in its sheer mass and magnetic fury. When this magnetized cloud reaches our planet, it does not hit a solid wall. Instead, it collides with Earth's protective magnetic bubble, the magnetosphere. The impact compresses the day side of our magnetic field and transfers energy into it, sparking dazzling auroras near the poles as charged particles funnel down magnetic field lines. But the consequences can be far more serious. The rapid shifts in the magnetosphere induce powerful electrical currents in the ground itself, which can overload power grids, causing widespread blackouts. The surge of particles can damage satellites, disrupt radio communications, and pose radiation risks to astronauts. This is space weather, and its source is the sun's ability to accelerate matter to incredible speeds. We are living in the blast zone of a variable star, protected only by our thin magnetic shield, witnessing in real time how the transfer of energy through velocity shapes the very environment of our solar system. The violence of a solar flare is a local phenomenon, a mere spark compared to the truly cosmic detonations that can shake the fabric of our galaxy. Among the dead stellar remnants we have met, the pulsar, there exists an even more extreme and volatile cousin, the magnetar. Picture a neutron star, that city-sized ball of degenerate matter, but now imbue it with a magnetic field of almost incomprehensible power. A typical neutron star's magnetic field is already 1 trillion times stronger than Earth. A magnetar's field is another 1,000 times stronger than that. If a magnetar were located halfway between Earth and the Moon, its magnetic field would be strong enough to erase the data from every credit card on our planet. This unimaginable tension, this magnetic energy stored in the star's rigid crust, creates a ticking time bomb. The crust of a neutron star is not a smooth surface. It is a lattice of atomic nuclei under immense strain, a landscape of mountains no taller than a millimeter but with the mass of entire mountain ranges. As the magnetar's unimaginably powerful magnetic field slowly twists and evolves, it stresses this crust to the breaking point. Eventually, something has to give. The crust cracks. This is a starquake, but this is no planetary tremor. The energy released in this single, catastrophic event is more than our Sun will emit in 100,000 years, all unleashed in a fraction of a second. The sudden fracture causes a massive rearrangement of the magnetic field lines, which in turn accelerates electrons and other particles to nearly the speed of light almost instantaneously. The result is a giant flare, a burst of high-energy gamma rays and X-rays so brilliant it can, for a fleeting moment, outshine every other source of gamma rays in the entire Milky Way galaxy. This flash of radiation traveling outward at light speed is a transient beacon of a stellar catastrophe. We have witnessed these events. In December 2004, a magnetar in our galaxy, located about 50,000 light-years away, unleashed a flare so powerful that it actually compressed Earth's ionosphere, the upper layer of our atmosphere, despite being on the far side of the galactic center from us. For 1/10 of a second, it was brighter than the full moon in gamma rays, and its effects were measurable from a distance of half a galaxy. These starquakes are the ultimate demonstrations of magnetic fury, proving that even in the cold, dense corpses of dead stars, the universe retains a capacity for sudden, explosive violence, sending its message across the light years at the only speed such urgent news can travel, the speed of light itself. But even the magnetar's brilliant flash is a local event compared to the true titans of cosmic violence. For a few seconds, these events outshine every other source of gamma rays in the entire observable universe. They are gamma-ray bursts, the most powerful explosion since the Big Bang itself. Their story begins in the final moments of a star many times more massive than our Sun. When such a star exhausts its nuclear fuel, its core collapses catastrophically into a black hole or a magnetar. In that instant, a portion of the star's immense gravitational energy is channeled not into a symmetrical supernova, but into two narrow, opposing beams of ultra-relativistic material. These are the jets, and they are the heart of the phenomenon. The material within these jets, a plasma of electrons, protons, and atomic nuclei, is accelerated to velocities so extreme they are described by Lorentz factors in the hundreds. This translates to over 99.999% of the speed of light. It is the fastest bulk flow of matter we know of in the cosmos. The jet must drill its way out through the outer layers of the dying star, and when it finally breaks free, it produces the initial blinding flash of gamma rays we detect. This is a long-duration gamma-ray burst, a stellar death cry that can last from 2 seconds to several minutes, and it is a direct beacon to the birth of a new black hole. There is a second, even more exotic trigger. When two ultra-dense neutron stars spiral together in a final, decaying orbit, their collision also forges a black hole and launches similar, unimaginably fast jets. This produces a short-duration gamma-ray burst, a flash lasting less than 2 seconds, but one that also creates ripples in spacetime itself, gravitational waves we can now detect. In both cases, the physics is pushed to the absolute limit. The particles in those jets are moving so close to light speed that time, for them, is dramatically slowed. Their journey across thousands of light years is, from their own perspective, nearly instantaneous. The energy released is staggering, more than our Sun will emit in its entire 10 billion year lifetime, focused into a beam narrower than a few degrees. If one of these beams were pointed directly at Earth from within our galaxy, the effects would be catastrophic for life, stripping our ozone layer and triggering a mass extinction. Thankfully, they are rare and distant. We see them only because we lie in the line of fire of a jet from a cataclysm occurring in a galaxy billions of light years away. Each brief, brilliant flash is a postcard from the edge of physics, a testament to the universe's capacity for focused, relativistic fury, and a reminder that the fastest things are often born from endings of the most spectacular kind. The energy of those cataclysmic collisions does not vanish into the void. It radiates outward in a form more fundamental than light. When two black holes or neutron stars spiral together in their final dance, they do not just send matter flying, they shake the very fabric of the cosmos. Their immense masses, whirling at a significant fraction of light speed, warp the spacetime around them. As they merge, this violent motion creates ripples in spacetime itself, waves of gravitational distortion that propagate outward in all directions. These are gravitational waves, and they are not made of matter or light. They are traveling distortions of geometry, stretching and squeezing the distance between objects as they pass through them. Most profoundly, these ripples travel at the speed of light, the ultimate speed limit for information in the universe. This was a key prediction of Einstein's theory of general relativity, but for a century it remained just a theory because the effect is incredibly tiny. The distortion caused by even the most powerful cosmic events is minuscule by the time it reaches us, changing the distance between objects by less than the width of a single proton. Detecting such a faint whisper required one of the most sensitive experiments ever built, the Laser Interferometer Gravitational Wave Observatory, or LIGO. Its design is elegant in its simplicity. Two long, perpendicular arms, each 4 kilometers long, house lasers bouncing between mirrors in a vacuum. A passing gravitational wave will ever so slightly lengthen one arm while shortening the other. By monitoring the laser light in these arms with exquisite precision, scientists can detect that infinitesimal change. On September 14, 2015, LIGO made its first historic detection. The signal, named GW150914, was the unmistakable chirp of two black holes, each about 30 times the mass of our Sun, merging over 1.3 billion light-years away. The waves carried the precise signature of their final, frantic orbits and collision, confirming not only their existence but also that they traveled at the speed of light. This opened an entirely new sense for astronomy. Before this, we observed the universe almost entirely through light across the electromagnetic spectrum. Now we can listen to it through vibrations in spacetime itself. This new window is perfectly tuned to the universe's fastest, most violent events, the mergers of compact objects like black holes and neutron stars that accelerate matter to relativistic speeds. Each detection is a direct recording of gravity in its most dynamic and extreme state, a soundtrack written in spacetime, arriving at our doorstep at the universe's maximum possible speed. But those gravitational waves are not the only strange signals echoing across the cosmos. From the deep dark between galaxies come flashes of radio energy so brief they were almost mist and so powerful they defy easy explanation. These are fast radio bursts, or FRBs. Imagine the entire energy output of our Sun over nearly a century, released in a single, blinding millisecond. That is the raw power packed into these enigmatic pulses. They travel billions of light years to reach us, stretching and dispersing through the thin plasma of intergalactic space along the way, which allows astronomers to use them as probes to weigh the unseen matter in the cosmos. Yet their origin remained one of astronomy's greatest puzzles for over a decade. The leading theories all point back to the universe's most extreme objects and the relativistic speeds they generate. One compelling explanation involves magnetars, those neutron stars with unimaginably strong magnetic fields. A starquake on a magnetar in a distant galaxy could produce a blast of energy that manifests as a one-time FRB. We actually have evidence for this. In April 2020, a magnetar within our own Milky Way emitted a radio burst that, while much weaker, shared striking characteristics with the extragalactic FRBs we see. But some FRBs are even stranger, they repeat. This rules out any one-time cataclysm like a collision or explosion. For a repeating signal, astronomers look to an object that can produce multiple bursts without destroying itself. One fascinating model involves a highly magnetized neutron star orbiting a massive, hot star. As the neutron star plows through the dense stellar wind of its companion, immense shocks form, accelerating particles to near light speed and generating those brilliant, repeating radio flashes. Another possibility points to the violent environment around a newborn black hole, where collapsing stellar material or interacting magnetic fields could create the conditions for these intense pulses. What all these theories share is a requirement for extreme physics, environments where matter is moving at a significant fraction of light speed, where magnetic fields are trillions of times stronger than Earth's, and where gravity warps spacetime itself. Each fleeting millisecond burst is a coded message from a realm of ultimate velocity and density, a brief open window into processes we are only beginning to understand. They are not just cosmic mysteries, they are stopwatches ticking at the edge of physics, reminding us that the universe's fastest engines are still talking, if we can only learn to listen. These fleeting radio whispers hint at a far more sustained and powerful force, one that can dictate the very fate of an entire galaxy. At the heart of the most luminous objects in the universe, quasars, a different kind of wind blows. A quasar is the visible, blazing signature of a supermassive black hole in a feeding frenzy, so bright it can outshine the combined light of every star in its host galaxy. This incredible radiation does not merely illuminate, it exerts pressure. The torrent of photons pouring from the accretion disk slams into the surrounding clouds of gas and dust with immense force, not unlike the solar wind but on a truly monstrous scale. This radiation pressure drives colossal outflows, vast rivers of superheated material streaming away from the galactic core at astonishing velocities. We are not talking about a gentle breeze, but a hurricane of cosmic proportions, with these quasar winds reaching speeds between 20 and 30% of the speed of light. That is millions of kilometers per hour, a continuous, high-velocity gale powerful enough to sweep an entire galaxy clean. This process is a breathtaking display of feedback, a self-regulating mechanism built into the cosmos. The black hole feeds, it shines brilliantly, and that very brilliance pushes away the fuel that feeds it. But the impact goes far beyond simply starving the central engine. These relativistic winds tear through the galaxy's reservoirs of cold gas, the very raw material needed to form new stars. By heating and dispersing this gas, the quasar wind can effectively shut down star formation across vast regions, putting a premature end to a galaxy's growth. This is why astronomers believe these ultra-fast outflows are crucial architects in the story of galaxy evolution. A quasar's brief, brilliant phase of activity, powered by its incredible speed, can leave a permanent mark, transforming a vibrant, star-forming spiral into a quiet, aging elliptical galaxy. The evidence is written across cosmic time in the correlation between the masses of black holes and the properties of their host galaxies. It suggests a profound dialogue where the fastest, most energetic processes at the smallest scales, right around the event horizon, dictate the destiny of the largest structures we can see. The quasar wind is the voice in that conversation, a supersonic command that echoes for billions of years. Yet the fastest motion in the cosmos involves no object moving through space at all. The fabric of the universe itself is stretching, carrying galaxies along for the ride in a grand exodus we call the expansion of space. This was the monumental discovery of astronomer Edwin Hubble in the 1920s. By measuring the light from distant galaxies, he noticed a consistent, startling pattern. Their light was shifted toward the red end of the spectrum, and the farther away a galaxy was, the greater this redshift became. This was not a Doppler shift from motion through space like the sound of a receding train. This was something far more profound. The very wavelengths of light were being stretched as they traveled across an expanding universe. Hubble formulated this into a simple, powerful law. The recessional velocity of a galaxy is directly proportional to its distance from us. This means a galaxy twice as far away is moving away twice as fast. This relationship holds true no matter where you are in the universe. Every observer would see the same thing, galaxies fleeing from them, with the most distant ones receding the fastest. This leads to a mind-bending consequence. Because the speed increases with distance, there is a boundary, a sphere around any observer called the Hubble sphere. For galaxies beyond this sphere, the expansion of space between us and them adds up to a recessional velocity that exceeds the speed of light. This seems to shatter the cosmic speed limit, but it does not. Here is the crucial distinction. Relativity forbids any object from moving through space faster than light. But this is not motion through space. It is the space itself that is growing, carrying the galaxies apart. They are, from their own local perspective, at rest. The distance between us is simply increasing because there is more and more space appearing in between. Think of dots on an inflating balloon. As you blow it up, each dot sees all the other dots moving away, but no dot is actually traveling across the surface of the balloon. The rubber itself is stretching, so a galaxy whose light left it billions of years ago can now be receding from us faster than light, its light still struggling across an ever-widening gulf. This expansion is the ultimate silent engine behind the greatest speeds we can measure, a background hum of creation that sets the stage for every other race across the cosmos. Yet even our grandest cosmic velocities can be measured on a more intimate scale, with machines built by human hands. Our fastest spacecraft are triumphs of engineering, yet their speeds reveal the humbling gap between our reach and the universe's true scale. Consider the Helios probes launched in the 1970s to study the Sun. Using a slingshot maneuver around our star, they reached speeds over 250,000 kilometers per hour, setting a record that stood for decades. That record now belongs to the Parker Solar Probe, a mission designed to touch the Sun. It uses a series of gravity assists around Venus to fall ever closer to our star, and at its closest approach, the Sun's immense gravity accelerates it to a staggering 690,000 kilometers per hour. That is 0.064% of the speed of light, fast enough to travel from New York to Tokyo in under a minute. This makes it the fastest object humanity has ever created. Then there is Voyager 1, our most distant emissary. While its raw speed, about 61,000 kilometers per hour, is slower, its achievement is one of persistence. It has been traveling for over 45 years, crossing into interstellar space, carrying a golden record of sounds and images from Earth. These probes represent the pinnacle of our technological ambition, moving at velocities that feel incomprehensible on our human scale. Yet when we place them against the cosmic speeds we have explored, the contrast is stark. Parker Solar Probe's blistering pace is still over 1,500 times slower than the speed of light. It would take this fastest human object approximately 6,500 years to reach even the nearest star system, Alpha Centauri. Our spacecraft are like ants crawling across a continent, while neutron stars and hypervelocity stars are supersonic jets screaming overhead. This gulf is not a failure, it is a map of a frontier. It defines the challenge of interstellar travel and underscores a profound truth. The natural universe operates on an entirely different tier of energy and velocity. forged in gravity wells and magnetic furnaces we can only observe from a vast and silent distance. But this silent river of expansion is not the only invisible current moving through the cosmos. There is another, more ghostly tide, one composed of particles so elusive they can pass through light years of solid lead without a single interaction. These are neutrinos, and they are the universe's ultimate spectral speedsters, born in the nuclear furnaces of stars, in the violent hearts of supernova, and even in the gentle decay of elements deep within the Earth. Neutrinos are produced in staggering numbers. Trillions pass through your body every second, day and night, completely unnoticed. For decades, physicists believed these ghostly particles were massless, like photons, and thus should travel at exactly the speed of light. But nature, as it often does, held a subtle and profound surprise. The key to unlocking this mystery lies in a strange quantum behavior called neutrino oscillation. As they travel through space, neutrinos can spontaneously change their identity, morphing between three different types or flavors. This remarkable transformation is only possible if neutrinos have mass, however infinitesimally small. A massless particle, locked into the speed of light, experiences no passage of time from its own perspective, and therefore cannot change. The fact that neutrinos oscillate proves they do experience time, which means they must travel just a tiny fraction slower than light. Their mass is incomprehensibly small, millions of times less than an electron, but it is not zero. This tiny deviation from light speed became a critical, observable test during one of modern astronomy's most famous events. In February 1987, a star exploded in our neighboring galaxy, the Large Magellanic Cloud. This was supernova 1987A, the closest such explosion in centuries. Hours before the visible light from the blast reached Earth, vast underground detectors in Japan and the United States registered a sudden, brief pulse of 24 neutrinos. These ghostly messengers had outraced the photons, escaping the collapsing stellar core unimpeded while the shockwave was still fighting its way out through the star's outer layers. By comparing the arrival time of the neutrinos with the first flash of light, scientists could perform a direct cosmic experiment. They confirmed that the neutrinos had traveled for 168,000 years at a velocity indistinguishable from, but measurably less than, the speed of light. That minuscule difference over that immense distance was the fingerprint of their tiny mass. This observation was a triumph, not just for astrophysics, but for our fundamental understanding of the universe. It proved that the standard model of particle physics, which long assumed neutrinos were massless, was incomplete. These nearly massless, nearly light-speed phantoms are now key to probing the most extreme environments, from the cores of distant quasars to the aftermath of the Big Bang itself, carrying secrets from places light cannot immediately escape. The journey to near light speed often begins not with a sudden blast, but with a slow, inevitable spiral into a cosmic whirlpool. This is the accretion disk, a frenzied maelstrom of superheated gas and dust caught in the fatal grip of a black hole or a neutron star. Picture a vast, flat, rotating river of matter, trillions of miles across, glowing with the ferocious heat of creation itself. Material in this disk does not fall straight in, any more than water rushes directly down a drain. Instead, it follows a long, doomed orbit, spiraling inward over thousands of years. This spiral is the key to its incredible energy. Particles of gas on slightly different orbits rub against each other, creating immense friction. This friction converts the gravitational energy of the fall into heat, raising temperatures to millions of degrees, causing the disk to blaze across the spectrum from X-rays to visible light. But friction is only part of the story. The disk is also threaded with powerful, tangled magnetic fields generated by the swirling plasma itself. These fields act like cosmic stirrers and slingshots. They create turbulence that helps transfer angular momentum outward, allowing more material to spiral inward, and they can also fling charged particles away at tremendous speeds. As matter gets closer to the central object, the pace becomes frantic. Orbital velocities in the inner regions of the disk reach a significant fraction of light speed. For a stellar mass black hole, the innermost stable orbit can see material whirling at over half the speed of light. This is not a serene glide. It is a chaotic, violent ballet where magnetic forces whip particles to relativistic energies, creating jets and coronas of even hotter plasma above and below the disk. The intense radiation we observe from quasars and active galactic nuclei, the brilliant X-ray binaries in our own galaxy, all that light is the final scream of this matter, a beacon of its conversion from mass into energy through velocity and friction. The accretion disk is the universe's ultimate power plant, where gravity's relentless pull is transformed into the blinding light and high-speed particles that signal the presence of the cosmos's most enigmatic objects. The aftermath of such a cataclysm is where the universe performs its most dazzling alchemy. When two neutron stars finally merge, the resulting explosion is not called a supernova but a kilonova. In this brief, brilliant flash, lasting only days, the conditions are so extreme that they forge the heaviest elements in the cosmos. The immense gravitational and nuclear forces at play do not just create a black hole, they also blast a fraction of the neutron-rich material out into space in powerful, fast-moving winds. These are the kilonova ejecta, and they are the universe's foundries for gold, platinum, uranium, and other rare, heavy elements. The physics is staggering. The material ejected is not a gentle puff. It is hurled outward by the intense neutrino flux and the violent dynamics of the merger at velocities between 20 and 30% the speed of light. That is hundreds of millions of kilometers per hour. At such incredible speeds, this enriched material can rapidly travel far from the site of the collision, seeding the surrounding interstellar medium with its precious cargo. For decades, astronomers wondered where in the universe elements heavier than iron were created. Ordinary stellar fusion cannot produce them, and core collapse supernovae were thought to be the primary source, but the numbers never quite added up. The direct detection of a kilonova in August 2017, accompanying the gravitational wave signal from a neutron-star merger, provided the definitive answer. The observed light from that event carried the unmistakable spectroscopic signature of heavy elements being synthesized in real time, a process called rapid neutron capture. In that single event, an amount of gold many times the mass of our entire planet was likely forged and scattered. This changes our perspective on the very stuff of our world. The gold in a wedding ring, the platinum in a catalytic converter, the uranium that fuels reactors, these are not ancient relics from the birth of the universe. They are quite literally stardust, but of a very specific and violent kind. They are the ashes of a cosmic collision that happened billions of years ago, ejected at relativistic speeds from a dying binary system, eventually finding their way into the nebula that formed our solar system. Our connection to the cosmos is not merely symbolic, it is material, written in the atoms forged in the fastest, most violent crucibles imaginable. But the full, terrifying power of a relativistic jet is usually hidden from our view, angled away into the depths of space. There is a special case, however, where our cosmic vantage point gives us a front-row seat to the ultimate particle beam. When the supermassive black hole at the heart of an active galaxy has one of its jets pointed almost directly at Earth, we do not see a distant, side-on fountain. We stare straight down the barrel of the universe's most powerful cannon. This object is called a blazar. The alignment is everything, because the material in that jet is racing toward us at over 99% of the speed of light. A strange consequence of Einstein's relativity takes over, an effect called relativistic beaming. All the light and radiation produced by the jet, which would normally be emitted in all directions, gets squeezed and focused into a narrow cone pointing in the direction of motion. It is like the headlight of a train approaching at nearly light speed becoming blindingly bright, while the light trailing behind it grows dim. For us, positioned within that cone of concentrated radiation, the blazar does not just look bright. It appears millions of times brighter than it would if the jet were pointed even slightly away from us. This amplification makes blazars the most persistently luminous objects in the known universe, often outshining their entire host galaxies. The relativistic beaming creates another, even more startling illusion. We can track bright knots of plasma within the jet as they move, because the material is coming almost directly at us at such a fantastic fraction of light speed. The light emitted later from a knot has less distance to travel to catch up to the light it emitted earlier. This compresses the time between events we observe, making it appear as though these plasma blobs are moving across the sky at many times the speed of light. This apparent superluminal motion is a perfect, observable confirmation of relativity in action, a cosmic mirage born from extreme velocity. Observing a blazar is not like watching a distant firework, it is like peering directly into the nozzle of a hydroelectric turbine at the moment it turns on. The intense, variable light we see, from radio waves to the highest energy gamma rays, carries the direct, unfiltered signature of processes happening just outside the black hole's event horizon. Every flare and flicker is a message from the edge of physics, a real-time report on how matter behaves when accelerated to the absolute limit. In this unique alignment, the universe offers us a rare gift, a clear and magnified view into the heart of its fastest engine. Even the quietest stars can harbor the potential for the most violent rebirth. Our journey has taken us to black holes and neutron stars, but there is another, more common stellar corpse whose demise lights up the cosmos in a very specific and useful way. This is the white dwarf, the Earth-sized remnant of a star like our Sun after it has exhausted its nuclear fuel. For billions of years, these dense, cooling embers simply fade into the dark. But if a white dwarf has a companion, its story may not be over. In a close binary system, two white dwarfs can begin a slow, fatal dance. Emitting gravitational waves, they lose energy and spiral inward over eons, their orbital period shrinking from years to minutes. In their final moments, these two degenerate spheres of carbon and oxygen whip around each other at orbital velocities reaching thousands of kilometers per second. This is not a gentle merger. The collision is so violent and sudden that it triggers a runaway thermonuclear fusion reaction, incinerating both stars completely in a few seconds. The resulting explosion is a Type Ia supernova, one of the most energetic events in the universe. What makes this particular explosion so crucial for cosmology is its remarkable consistency. Because the explosion always occurs when the merging white dwarfs reach a specific critical mass, the peak brightness of these supernovae is nearly identical every single time. This makes them perfect standard candles, cosmic lighthouses of known intrinsic brightness. By measuring how dim they appear from Earth, astronomers can calculate their distance with incredible precision. It was observations of distant Type Ia supernova in the late 1990s that led to the groundbreaking Nobel Prize-winning discovery that the expansion of the universe is not slowing down but accelerating, driven by a mysterious force we now call dark energy. So, from the ultra-fast, cataclysmic merger of two dead stars, we gain a ruler to measure the cosmos itself. Their final, brilliant flash, born from incredible orbital speed, becomes a beacon that illuminates the fate of everything. This complex motion of our galaxy is not just a pull toward massive clusters, but also a push away from cosmic emptiness. The universe's large-scale structure resembles a vast sponge, with dense filaments and clusters of galaxies surrounding enormous, nearly empty bubbles known as voids. These voids are not simply passive gaps, they are dynamically expanding. With very little matter inside to provide gravitational attraction, the relentless expansion of space acts almost unopposed within them, causing these regions to grow faster than the universe's average rate. We live on the edge of one such immense emptiness called the local void. a region hundreds of millions of light-years across that contains almost no galaxies. Think of it as a cosmic vacuum, and our local group of galaxies is like a collection of objects sitting on the rim of that expanding bubble. The void's rapid growth exerts a subtle but significant repulsive effect, essentially pushing our galactic neighborhood away from the emptiness and adding another powerful vector to our already complicated journey. This push from nothingness combines with the pull from the Great Attractor and the Shapley supercluster, creating the high peculiar velocity we measure for our local group. It is a profound reminder that in cosmology, absence can be as influential as presence. The forces shaping our path are not only the immense gravitational wells we are falling toward, but also the growing voids we are fleeing. The silent rivers of intergalactic space are not empty, they are highways for immense, invisible clouds of primordial gas. One of the most famous of these travelers is the Smith Cloud, a colossal streamer of neutral hydrogen over 11,000 light-years long and 2,500 light-years wide, discovered by astronomer Gale Smith in 1963. It is not orbiting peacefully with the rest of the Milky Way's disk. It is a runaway hurtling toward our galaxy at nearly 300 kilometers per second. At that speed, it could cross the entire United States in just about 10 seconds. This is not a gentle approach, it is a high-velocity collision course. Current observations show the cloud is on a return path, having passed through the outskirts of our galaxy once before, and is now on a trajectory to slam back into the Milky Way's disk in roughly 30 million years. But where did such a massive, fast-moving structure come from? Astronomers have debated two leading possibilities. The first is that it is tidal debris, a long streamer of gas ripped from a smaller satellite galaxy as it was torn apart by the Milky Way's gravity over billions of years. The cloud's trajectory and chemical composition, which shows a lower abundance of heavy elements compared to our galaxy's gas, support this extragalactic origin story. It would be a ghostly remnant of a cannibalized dwarf galaxy, its stars long since scattered, but its gas still tracing a mournful orbit. The second theory suggests a more explosive birth within the Milky Way itself. Perhaps it was a massive bubble of gas blown out from the galactic disk by the combined force of multiple supernova or stellar winds, a galactic fountain that launched material high above the plane, only for it to cool, condense, and now fall back in a deadly rain. Regardless of its origin, the Smith Cloud's fate is sealed and spectacular. When it impacts the galactic plane, the collision will be a slow-motion cataclysm of cosmic proportions. The immense pressure of plowing into the Milky Way's own gas will trigger shockwaves that ripple through the interstellar medium, compressing vast regions and lighting the fuse for a new wave of star formation. The cloud carries enough gas to form over 2 million new suns, a future stellar nursery delivered at bullet speed. This incredible object teaches us that a galaxy is not an isolated island. It is an active participant in a dynamic ecosystem, constantly accreting, recycling, and expelling material. The Smith Cloud is a messenger from that cycle, a herald of both a violent past and a creative future, reminding us that even the fastest, most solitary travelers in the dark are destined to become part of something new. The violence of a black hole is not limited to its jets or the silent mergers of its kin. Its gravitational reach can reach out and seize a passing star, tearing it apart in a spectacle of cosmic destruction. This is a tidal disruption event, one of the most dramatic single acts in the universe. It begins with an ordinary star, much like our own sun, on a long, looping orbit around a supermassive black hole at the center of its galaxy. Over millions of years, gravitational interactions with other stars may nudge its path, sending it on a trajectory that brings it perilously close to the black hole's event horizon. The star crosses a critical boundary known as the tidal radius, where the black hole's gravity becomes stronger than the star's own self-gravity. This is the point of no return. The side of the star facing the black hole feels a much stronger gravitational pull than the side facing away. This difference in force, the tidal force, stretches the star horizontally while compressing it vertically. The star does not simply fall in, it is pulled into a long, thin strand of superheated plasma, a process literally called spaghettification. In a matter of hours, the star is completely shredded. Roughly half of its material is flung away from the black hole at tremendous speeds, ejected in fast-moving streams that carry the star's legacy out into the galactic void. The other half, however, remains bound to the black hole. This material does not vanish immediately. Instead, it forms a chaotic, swirling maelstrom, a temporary accretion disk that orbits the black hole at velocities approaching a significant fraction of light speed. The friction and collisions within this sudden, dense disk of stellar debris heat it to incredible temperatures, causing it to shine with the brilliance of billions of stars, emitting a tremendous flare of light across the electromagnetic spectrum. For a few months, this flare can outshine the combined light of every other star in its host galaxy, a brilliant funeral pyre for a sun that wandered too close. Astronomers have now observed dozens of these events, each one a unique laboratory. By studying the light curve and the spectrum of the flare, scientists can weigh the black hole, understand the composition of the devoured star, and witness the real-time formation of an accretion disk from its very first moments. A tidal disruption event is a fleeting but brilliant chapter, a stark demonstration of gravity's absolute dominion, where an entire solar system's potential future is converted, in a flash of light and speed, into a final, dazzling message. Sometimes the most profound cosmic mysteries are not found in distant galaxies, but in the quiet hum of our own spacecraft. For decades, a tiny, persistent puzzle haunted the trajectory of two of humanity's most distant robotic explorers, Pioneer 10 and Pioneer 11. These intrepid probes, launched in the early 1970s, were the first to visit the outer planets and the first to be placed on trajectories that would carry them out of the solar system entirely. As they journeyed into the dark, mission controllers tracked their positions with exquisite precision using radio signals. Over the years, a minuscule discrepancy emerged, an anomaly so small it was almost easy to dismiss. The pioneers were slowing down ever so slightly more than the laws of gravity predicted. They were experiencing a tiny, constant deceleration back toward the sun, a mysterious drag equivalent to just 10 billionths of the force of gravity we feel on Earth. This was the Pioneer anomaly, a ghostly tug that defied explanation for over 30 years. Was it a sign of new physics? Could it be the gravitational pull of unseen dark matter in our solar system, or perhaps a subtle flaw in our understanding of gravity itself at very large scales? The idea captured the imagination of scientists and the public alike, a whisper that our most fundamental theories might need revision, all hidden in the precise measurement of a spacecraft's speed across billions of miles. The solution, when it finally came, was not a revelation of new cosmic laws, but a masterclass in meticulous engineering detective work. A dedicated team of researchers spent years recovering old data tapes, reconstructing the probe's thermal models, and accounting for every conceivable force. The culprit was not a shadowy substance or a crack in relativity. It was heat, specifically, the anisotropic radiation of heat from the Pioneer's radioisotope thermoelectric generators. These nuclear power sources, which provided electricity by converting heat from radioactive decay, kept the spacecraft warm. That heat radiated away into space, but not perfectly evenly. A slightly greater amount of infrared photons were emitted from the warm back of the spacecraft's dish antenna, which faced toward the sun, than from the cooler front. According to the simple law of conservation of momentum, every photon carries a tiny amount of momentum. The slight imbalance in this thermal radiation acted like a very weak but very constant rocket engine pushing the spacecraft back toward the sun. Once this subtle effect was precisely quantified and accounted for, the anomalous deceleration vanished. The Pioneer anomaly was solved. This episode stands as a powerful lesson in the scientific process and the incredible precision of modern celestial navigation. It reminds us that the universe often speaks in the faintest of whispers, and that understanding the true speed of an object, even one built by human hands, requires accounting for every last whisper of force, no matter how small. These incredible velocities are not just numbers on a page, they warp reality itself. For any object moving at a significant fraction of light speed, the universe as we know it begins to unravel in profound and measurable ways. This is the realm of Einstein's special relativity, where speed transforms from a simple measurement into a sculptor of spacetime. The faster you move through space, the slower you move through time relative to a stationary observer. This is time dilation. For a pulsar streaking across the galaxy at 99% of light speed, or a proton in a quasar jet, a single second of their experienced time might stretch into many seconds or even years for us watching from a distance. Their clocks literally tick slower. Alongside this temporal stretching comes a spatial squeeze, length contraction. From our perspective, the relativistic object itself appears compressed along its direction of motion, becoming shorter and more dense. These are not illusions or mathematical tricks, they are verified physical consequences. Particles in our largest accelerators, moving at over 99.99% of light speed, have measured lifespans extended thousands of times longer than their stationary counterparts, precisely as relativity predicts. The energy required to push matter even closer to that ultimate barrier becomes astronomical, climbing toward infinity. This is why the natural particle accelerators around black holes are so vital. They provide gravitational and magnetic forces on a scale we could never replicate, doing the universe's most extreme work. These relativistic effects collectively define the very boundaries of our knowledge. Because the universe is expanding, and that expansion carries distant galaxies away faster than light, there exists a cosmic horizon, a sphere beyond which we can never receive any new information. The light from those ultra-distant regions will simply never reach us, as the space between us stretches faster than the light can traverse it. Our observable universe is therefore finite, not because it ends, but because the speed of light imposes a fundamental limit on what we can ever see. Every fast-moving object we have explored, from hypervelocity stars to gravitational waves, operates within this cosmic theater, its behavior and its very existence dictated by the elegant, unbreakable laws that bind speed, time, and space into a single dynamic fabric. Speed is far more than a simple measurement. It is the universe's primary language of energy. From the ghostly whisper of a neutrino to the silent expansion of space itself, velocity defines how matter behaves, how light travels, and how structures evolve across cosmic time. This journey through the fastest objects reveals a cosmos in constant, dynamic motion. A place where the extremes of speed are not anomalies but fundamental expressions of the laws of physics. Each hypervelocity star, each relativistic jet, each gravitational wave is a piece of a larger puzzle, demonstrating how energy is transferred and transformed on the grandest scales. By studying these ultimate speed demons, we are not just cataloging impressive numbers, we are stress-testing our understanding of reality. We push Einstein's theories to their limits, probe the nature of dark matter and dark energy, and witness the raw power of creation and destruction. Every new detection, whether a fast radio burst from a distant galaxy or the precise trajectory of a spacecraft, adds another line to this story. The quest to understand cosmic speed is far from over. It is an ongoing detective story written across the entire electromagnetic spectrum and now through the ripples in spacetime itself. If these explorations of the universe's fastest mysteries captivated you, consider subscribing to the channel. Your curiosity fuels this journey of discovery, and together we can continue to unravel the secrets hidden in the silent, swift dance of the cosmos.